Hi guys, how's it going? Today we'll be solving validate binary search tree. It's a medium level problem on Leetcode. Let's read through the question now. Given a binary tree, determine if it is a valid binary search tree. Assume a BST is defined as follows. Left subtree of a node contains only nodes with the keys less than the node's key, the root node. The right subtree of a node contains only nodes with the keys greater than the node's key. Both left and the right subtrees must also be binary search trees. So this is a problem that have been given to us today. So let's see how we can solve this problem now. So given the cases are 2, left node is 1, right node is 3. Again, so this is 2, 1, 3. And the output is supposed to be true because the left node is 1, the right node is 3. It comes out to be a valid binary search tree. For example 2, it's not a valid binary search tree. You can see it clearly. Its output is false because 1 is less than 5, 4 is not greater than 5. So this is not a valid binary search tree. So you guys will be thinking that it is a fairly simple approach maybe to solve this problem, and because we just have to check whether the current node's left node and the right node, so left node is less than the root node or the right node is greater than the root node. But that's not the point, because these two examples are not enough to actually explain the problem clearly. So let me just show you the examples that I've created. It's just one more case that I've created for you guys. So 2 and 3 you already seen, it's true, right? This one is the same as the one given in the question, case 2, and then there's case 3. Case 3 is with this 2, in the first subtree you have 2 which is less than 3, so yeah, it's valid. 5 which is greater than 3, yeah, it's valid. But coming down on this subtree, where is 2 is the root node or the parent node, 1 is less than 2, yes. 4 is greater than 2, yes. But it's still not a valid binary search tree because the keys on the left of the root node should all be less than the root node. So all the keys here, 2, 1, 4, should be less than 3. And all the keys on the right of 3, for in this case it's 5, or rest of the keys that might appear here, it should be greater than 3 as the root node. So this won't solve the approach that is like thinking of like simple checking of left and right would not work. So what we need to do is we kind of have to have a range check. If you can think of a recursive approach of just checking the parent node like 3 and checking in against the left and the right node, that might work in some cases like case 1 and case 2, but it would fail in this case. Or you have to have this information of the root node propagated down so that you can actually use it in comparison. So you have to do some comparisons while you are building the tree, and that would help us solve the problem. So now I'm thinking of the recursive solution that I can build. I'll just have a recursive solution function template. I'll call it like validate, which makes a lot of sense. Let's just return that, and then this validate would also be a boolean variable. So let's have root. As I discussed earlier, that we need to send to this recursive function a left check and the right check. So it helps to check the range, whether my current node lies in this range or not, because we can't just go about and check the parent node with if it is less than the left node and the right node only, which was very evident in the case 3. Let's have another node, but we don't have it right now, so it's just going to be null. And then we're going to create a validate function which will return boolean, right? So it will just have a node which will be like, I would say, root. It will have again a tree node, which will be, we can have it as a left one, and the tree node which can be the right one. So from time to time this right and left would change values. We'll just see. So now starting with the base case, let's write the base case. So if root of the recursive function equals to null, so just a piece of advice here, whenever you're starting write a recursive function, just trust that it works, right? Do not think that, or do not deep dive into thinking a lot on that function. Just think that it should work, and believing that it works, just first create the base case. So this is step 1 for any recursive function you're going to write. Yes, so if root equals to null, we'll just return true. That means because it's a valid binary search tree. That's if it is there's no node, it's still a valid binary search tree. There are two ways you can go about solving a recursive function. Is that either you can process till the end, or you can just terminate and return, let's say, false. So because this function can only return true and false, what we'll choose is like we'll have this function return just false whenever it encounters a condition, right? In this case, like 4 is greater than 3 in the case 3. So 4 is greater than 3. So you would definitely want to terminate the recursion here or return false, so that at the end the total result becomes false. It's just that we found just one instance of this binary search tree property not being followed, we just terminate everything, right? So it's just that when we find just one instance of this tree not following the binary search tree property, we'll just return false, and this would all entirely go out and return false in the end. So yeah, so if left is not null, so we have to evaluate that. We would not know when we are sitting on a root node that if it's the left being passed is null or not. So it's not checked till now. It's just we are doing that. So if left dot value, right? So left dot val, if the left dot value is greater than or equal to root dot val, right? Very simple check. You just return false. And if so, I'm very sure most of the guys would be thinking of that. This is very intuitive, obviously, because so you have that right dot equal to null, and then you have right dot val. If it is less than equal to what root dot val, you just go on and return false. And now, so now we're going to define how the left and the right subtree look like. I'll just call it the variable L, which represents the response from the recursive calls to validate the left subtree. So we're going to explore the left node, and again now, so I'm just going to define the template here. Right equal to validate root dot right, just that, right? So I have this template. So here we'll be passing the left node on the left, and the left node should be the one because keeping in mind the comparison. So what we're doing in the left side, if you see, we just have a maximum value as 3, and we want all the nodes on the left to be less than 3. So all we need is like we just keep the left as it is, and we keep on sending the root value, like the parent value, in the subtree or in the recursion, so that let's say 3 goes into the next level and 2 goes into the next level, just like that. So this keeps continuous relation in check, and that the left subtree should not be greater than the root. And similarly, if I have this as a right recursion, so I'll send it as root and right, because what I'm doing is like I'm just doing that all my nodes should be greater than the root node here, which is 3 here. So I have kind of a minimum limit, which is 3. So I'm putting it as the root node, which is 3, and minimum limit is 3, and all the nodes should be greater than the root node, which is, it goes into the right part. That is how it's supposed to be. And then we're going to return the response of the validation of the left subtree and the right subtree. Let's look on to how the recursion looks like, because it might be a little bit difficult for everyone to understand. So I've already created it for you guys, and so it starts with 3 null null. So I'm just sending 3 null null. So 3 null null, good enough. Then it goes on, it just validates root null. No, it's not null. It just says that left not equal, and it won't return false, right? Because it's a valid node, and it's a valid node on the right as well. So it just goes on. It just calls the validate on the left part first. This is root dot left left. So root dot left is 2, like on the left of 3 is 2. That is this call, and this is null. So we have been sending. So if you know that we are just reusing the left part which was sent, which was null here, and this is, so it still remains null. And then we just repeat the root because we want all the nodes on the left subtree less than 3. Similarly, it goes on again. On the left recursion, it calls it the root node is 1, which is the left node is 1. Then you have your null, which was again passed as a left node, which I have been passing here because we don't care about what the minimum value, how we want to see the node greater than form. All we need is like the maximum value, the node should be greater than on. So here the node should be greater than 2. That's what we have here. This returns true because this node is valid. So similarly, if we go on to the right part of 2 here, it goes on to like, because it's the right part, we'll send like root dot right, which was 4, and then you have the root node, which is 2. So you have the root node, and then the right part. The right we already have is 3, right? So you have a min check, or a check of a minimum value, that all the nodes on the right should be greater than 3. This condition wouldn't pass, because if you can see, the right should not be equal to null, and like if right is not null and right dot val is root dot val, it is true in this condition because right dot val is 3 and the root dot val is 4. So that it will return false here, and as we go on returning false on this part, this subtree becomes false, and when it goes back, after the call stacks start popping up, this complete tree becomes false. That's how this question can be solved. So now let's go on to submit the solution, and it's successful. Thank you for watching the videos, guys. If you really like the video, do like, do comment, and do subscribe to my channel.